Hi everyone, today I'm going to talk on interactive proof of proximity with Proof-Oblivious queries. This is a joint work with Oded Goldreich and Rothblum. Starting off, our work focuses on models, and as such, we'll need to define a baseline model to compare ourselves to and to build our definitions on, and this model will be of property testing. In property testing, we have a subset of strings of length n that we're interested in. We'll call it the property and denote it by pi. And we'll need to design what we call a tester, which will denote by t, which will get a query access to some input x, which means that it will be able to look at specific indices of x and read the bits. And our tester needs to satisfy two conditions. The first one is that if x is in the property, then we would like our tester to output yes with high probability. And otherwise, if x is far from the property, which means that the Hamming distance of x and any string in the property is large, then we want our tester to output no with high probability. In property testing, we want to minimize the number of queries that the tester makes to the input x, which we call a query complexity and denoted by Qt. A natural extension of property testing is the model of interactive proof of proximity, which I'll denote by IPP. In this model, we again have this interesting property pi, but now our tester will be called the verifier because now it is verifying. And additionally to same access to the input x, we now have a prover p, which knows the entirety of x, which is highlighted by the fact that p receives x as input, and v is able to communicate with p and ask it questions about x. As before, we want v, our verifier, to satisfy two conditions. The first one is if x is in the property, then we want that to exist some prover that will make our verifier say yes with high probability. And otherwise, if x is far from the property, like I defined in the property testing case, then we want, no matter what the prover will do, the verifier will output no with high probability. So the prover, even though it knows the entirety of x and v might not look at all positions of x, we want the prover not to be able to convince v to output yes mistakenly. Like in property testing, we're interested to minimize the number of queries that v makes to x, but now additionally we want to also minimize the number of bits communicated between v and p, and also a measure that we're interested in is the number of messages exchanged between v and p. And just to be clear about it, in this picture we have v and p communicating 3 messages, and although each message can contain some number of bits, not necessarily one. So these are two different measures, but they are connected. So a natural question to ask is, well, okay, we added a prover to the equation, and now did we really increase the power of the model? And specifically, we would like to show an exponential gap between property testing and interactive proof of proximity, which means to show a specific property for which we have a specific interactive proof of proximity, such that the query complexity times the communication complexity is exponentially smaller than the query complexity of any tester we can make for this property. And actually the question was already answered by Rothblum, Weizmann, and Weizmann, who also defined the model of interactive proof of proximity, and they show that yes, it is possible. They show an exponential gap. And furthermore, in another work, Goldreich and Rothblum show that we can show an exponential gap even when the prover is restricted to just send one message to v. So the whole communication is the prover sending one message to the verifier. And even under this restriction, we can already show an exponential gap, which means that the model of interactive proof of proximity is relatively powerful compared to property testing. So that's nice, and we'll note to focus on the verifier in interactive proof of proximity and highlight the fact that it engages in two inherently different types of activities. The first activity is querying x, which means looking at specific bits of x, but knowing that they are always correct. And the second activity is communicating with the prover p, who knows the entirety of x, but the prover may be untruthful. It can lie, even though it can answer very complicated questions about x. And interactive proof of proximity, we basically do not limit the amount of coordination we have between these two activities. We can maybe query X on some locations and then challenge P on these bits so that P will not be able to cheat. And the other direction, the prover may tell us, hey, look at the specific index of X, this is where you will find your answer, and we can do that. And our question, in our work, we asked the question whether this free coordination we have between these two activities is essential to get this gap, exponential gap between the power of inductive proximity and property testing. And a specific type of this restriction, which appears naturally in some cases, is the restriction of prover-oblivious queries. In this restriction, we limit the coordination, the possible coordination, in the direction of P2 querying X. In other words, this means that the queries that V makes to X can only depend on the internal randomness of the verifier and the input X. Whichever prover that we're talking with and whatever the prover says will not impact the positions we look at X in, and that's why it's called prover-oblivious queries. We make queries that are prover-oblivious. And I said that this is natural, so here's some motivation for this type of restriction. If we have a protocol in which the verifier makes prover-oblivious queries, the queries can be prepared in advance to the prover coming, even if the prover does not exist at this point and will come in the future and try to convince us that X belongs to some property, we can already ask the questions in advance. And another more practical one is in a work by Berman, Rothblum, and Weizmann and Nathan, which show that any interactive proximity which satisfies this prover-oblivious queries condition can be transformed to a natural notion of zero knowledge for this property. Okay, so we have this restriction that we're going to focus on, which is the prover-oblivious queries. And in order to talk about this more easily, we want to alter the model of interactive proof of proximity slightly. It will not decrease its power by what we call a verified decomposition. So we take our previously called verifier and we split it into three parts. The first part we'll call the querying part, which will be able to query X but not communicate with P. The second part is the interacting part, which will be able to communicate with P but not query X. And the third part is the decision part, which will receive the whole view of both the querying part and the interacting part, and we'll have to decide whether to output yes or no. And this whole box is what we previously called V, and so we decomposed V into three parts. And interactive proximity, we basically allowed a free communication between these two parts. And that's the way they were able to coordinate whatever they query to X or whatever they query to P. And just to be clear about it, I am not counting this communication inside the communication complexity. The complexities are still the same. The number of places that Q looks at X and the number of bits and messages communicated between I and P. To compare this to the prover-oblivious queries restriction, we limit this direction of communication between I and Q. If Q does not receive any information from I, then inherently the queries that Q makes to X must be prover-oblivious. Okay? Looking more thoroughly in the other direction of coordination between Q and I, we actually identified three different models of prover-oblivious queries. We sort of get this prover-oblivious queries hierarchy. So on one extreme, if we limit the communication completely in the either direction between Q and I, we end up with what we call the isolated model, in which Q and I are completely separate entities. We highlight it by showing that they're initiated with independent randomness rho Q and rho I. On the other extreme, if we do not limit at all what Q might send to I, we end up with a general prover-oblivious queries model, which is the strongest prover-oblivious queries model, in which Q can send anything it wants to I. So that means it can send its internal randomness, the queries it makes, and the answers to the queries. And interestingly, there is actually an intermediate model between these two models, in which Q and I only share a common randomness between them. We call this model a pre-coordinated model and denoted by the fact that they receive a shared randomness row between I and Q, but there is no other communication. So compared to the general Proof-Oblivious queries model, Q cannot send to I anything, so it cannot send the answers to the query it makes. Maybe some queries are determined by this shared randomness, but maybe some are determined by X, and I will not be able to know them. And compared to the isolated model, where Q and I were completely independent entities, now they can be dependent in some way based on this common randomness. So that's nice. We have some sort of hierarchy of Proof-Oblivious queries, and a natural question to ask at this point is whether the exponential gap that we have for interactive proof of proximity, which only required sending just one message between the verifier and the prover, also holds for this model, or did this restriction of Proof-Oblivious queries and furthermore restricting how Q and I coordinate severely limits their power. So I'm going to answer this question regarding the pre-coordinated model. So let's take the theorem showing an exponential gap in the pre-coordinated model. We're going to show to see a property pi that satisfies two conditions. The first one regarding testing says that any tester for pi must have query complexity which is omega of square root of n, which means that relatively any tester for pi must make many queries. In comparison, we're also going to show a pre-coordinated protocol for pi in which V and P, or rather I and P, communicate 3 messages for a total communication which is logarithmic in n, and the querying part will only query x at a constant number of positions. So comparing Q times C to this lower bound on the query complexity of any tester, we achieve an exponential gap for this property pi between the pre-coordinated model and the property testing model. So let's start with defining the property. So the property will consist of any string of the form UUVV, such that UV is any string of length n over 2. So a little visualization of how these strings in this property look like. So a string is in this property. If we can cut it in some position, not necessarily in the middle, such that the first part of the string is 2 consecutive identical strings, and the second part of the string is 2 consecutive identical strings. Okay, and why testing is hard? So actually this is already shown by a work of Alon, Krivalevich, Newman, and Zegedy, which show that any tester for this specific property must make relatively many queries to test, so at least square root n, and a little bit on why this property is difficult. So given a cut, we actually can easily test whether a string is in this property or not. What the tester will do, it will sample a random position in the string I, and now that we have I and the cut at 2u, we can already define the matching position of I in the other copy of the string that we found under the cut 2u. So if we query this location I, its matching position will be in the other copy of V. And we can ask a single question whether these the bits in these 2 locations are identical or not. But the issue for the tester is that it doesn't know where to cut the string. The string can be cut there and there and there. So in a sense, a tester will need to test all possible cuts in order to determine that a string is far from being in the property, which means that this property is relatively hard for testing. So the description of what I gave here for testing once you know the cut gives a very simple interactive proof of proximity for this property. So in this interactive proof of proximity, we have V and the prover. Prover will simply send the claimed correct cut to you to the verifier, and the verifier can do exactly as we said, a constant number of times, and check these pairs of matching positions to determine whether the prover cheated or is telling the truth. But the issue, at least for us, in this very nice interactive proximity, is that it's not proof-oblivious. We can't fit it in any of the three models that we described before. And why is that? So sampling at position I and querying at position I is indeed proof-oblivious, but the matching positions of I under the cut to U depend on the cut that the prover sends. If the prover would have sent a different cut, we would query the different position, and therefore this second query that we make is prover dependent. So we'll need to take this idea of the prover telling us the cut and change it by a little bit. So let me describe the pre-coordinated protocol for this property. So here we have QI, we have X query access to input X, and we can interact with the prover P. I will start by saying what the shared randomness in this pre-coordinated model is. So it will simply be a random index out of n, which will denote by little I, which both Q and I know. The querying part will very simply just query X at position I and get back X, the bit Xi. The interacting module will start communicating with P. We have three messages. Remember, we want to show the gap for three messages in the pre-coordinated model. And we'll start by the prover sending the cut to U, as with the interactive proof of proximity. So notice that at this point, what I knows, it knows little I, so it knows the position that Q would query X, and it knows the claimed cut position that the prover sent it. So at this point, I knows little I and the matching positions of little I under this cut to U, but the issue that it cannot communicate this matching position to Q in order for Q to query X1. So instead, we'll ask the prover to provide us this location. But the issue is that the prover may be cheating. So we need to do something smart. So we'll define I0 to be little I and I1 to be the matching position of I under the cut to U that the interacting mode part knows. And it will also flip a coin, which will denote by this B. And we'll send to the prover the index IB. So with probability half, we will send the index that we actually queried. And then with probability half, we'll send the matching position of this location. And the prover will have to send back a bit, which is supposed to be X at position IB. So finally, I'll have to say what the deciding part will do. So I and Q will send their views to the deciding part, which will simply test whether this bit that the querying part queried matches the bit that the prover sent at the end of the interaction. So why this protocol works? So let's start with the condition in which X is in the property. So if X is in the property, then there is some cut to U that satisfies this condition. The honest prover can simply send this correct cut, and then no matter which position we ask, I or the matching position of I, these two indices point at the same bit. So the prover can simply see this bit and send this bit back, and it will always be equal to the bit that we queried, and we will always accept. We will always say yes. In the other direction, if X is far from being in the property, this means that no matter which cut the prover claims to be the correct cut, with high probability over this index I that we sample, I and the matching position of I will point to two different bits. They will not agree because this X is far from being in the property. And the prover, when he gets this index that we asked it to provide, he doesn't know whether it's the index that we actually queried or the matching position of the index. The only thing he sees is two different bits. So it will have to, at best, guess which one we actually queried. And therefore, by checking whether this bit that the queried is equal to the bit that the prover provides, we'll catch a cheating prover with probability at least half. And we increase this to any constant higher probability by, instead of sampling just one I, we will sample a constant number of indices I. So let's go back to the theorem. We already showed that previous work showed the first part. The second part, we showed a pre-coordinated model, which we proved to be true. The querying model, we say, just queries x at positions I. We said that we want a constant number of these positions, which means that the querying complexity will be constant. And in the interaction, P and I exchange 3 messages. We satisfy this condition, and the things that they actually communicate. So 2U is just a size, which can be communicated in a logarithmic amount of bits. This is an index, which can also be communicated with a logarithmic amount of bits, and this is just 1 bit. So repeating this for a constant number of times, we get that the communication complexity is order of log n. So to wrap this theorem up, we showed a pre-coordinated protocol which shows an exponential gap between the pre-coordinated model and property testing. To finish up this talk, let's recall our 3 models here on the right side and try to answer the questions for all these models. Is there an exponential gap from testing? And I'm going to present this the answer to the question in this table. In the rows, we'll have our 3 models, and in our columns, we have the different number of messages that we allow I and P to communicate. And starting off, in one message, all of these models collapse to the same model, and in previous work, they collapse to the same model of Proof-Oblivious queries, and in previous work that I referenced earlier by Gur and Rothblum, they show that no matter what that there cannot be an exponential gap between the model of Proof-Oblivious queries and property testing. We extend this result for the entirety of the isolated model. So we show that no matter how many messages we allow I and P to communicate inside the S, as long as we are in the isolated model, we cannot show an exponential gap from testing. So the isolated model is inherently as weak as property testing. We also show this result for the pre-coordinated model when I and P are limited to exchanging just 2 messages. And as I just proven in the theorem before, for 3 messages in the pre-coordinated model, we do have an exponential gap from testing. And in the general Proof-Oblivious queries model, we show that only 2 messages are enough to show an exponential gap. And now that we have this table on screen, let's recall that in interactive proximity, without this restriction of Proof-Oblivious queries, we just needed 1 message in order to show an exponential gap in the power of interactive proximity compared to property testing. Once we went into this Proof-Oblivious queries models, we needed to add at least 1 message in order to show a gap. And if we went further and limited the amount of coordination between these 2 entities Q and I, we needed 3 messages in order to show an exponential gap. And once we went to the extreme and completely disallowed the coordination between these 2 entities, we show that we weaken the model too much, and now it cannot be much stronger than property testing. So that's it, and thank you for listening.